This is the video on collisions. So before reviewing collisions, we just need to talk about momentum, right? So we've been learning about momentum, and momentum is the property of a body to keep moving. That's called momentum, right? So objects in motion remain in motion. That's called momentum. So this is the equation for momentum, right? It's the mass times velocity. The arrow above that P means that it's a vector quantity, so it has both direction and magnitude. And the unit for momentum is kilogram meters per second. So we also need to talk about impulse, right? So if we have momentum, how do you gain momentum? How do you lose momentum? You apply an impulse, right? So if you produce a change of velocity, you have to apply a net force. To produce a change of momentum, we apply what's called an impulse. Impulse is change of momentum. Impulse is force times the time interval. I apply a force for a certain amount of time. Well, that's going to give me my change in momentum. So we can put those equal to each other. So I can put the force times the time interval, the impulse, and my change in momentum is an object changing velocity. So all three of these equations are the same equation. So we talked about the 5 key components of impulse. Impulses always occur in pairs. Impulse pairs always are equal in magnitude. They're always oppositely directed. They always occur simultaneously, and they never cancel because they act on 2 different bodies. Very similar to the components of Newton's third law. So now that we know about momentum, let's answer this question. What happens to momentum during a collision? So in order to answer this question, we did coin collision. So this one's a real easy lab, right? All you do is you take 2 coins and you slide one into another. So you have a larger coin, a smaller coin. Doesn't matter which coin, but have a larger and a smaller one. So you just slide one into the other one. So let's just take a look at this, right? So during the collision, right, I'm sliding a penny into a quarter into a penny, doesn't matter. During the collision, they both apply the same force. That's what Newton's third law tells us. Now, during that collision, they both apply the force at the same time. That's what Newton's third law tells us. During the collision, well, they applied the force for the same amount of time, right? The same time interval. Uh, Now, this one's kind of tricky, right? During the collision, which coin experienced a larger impulse? Remember, impulse is force times the time interval that that force is applied. So we've already established that according to Newton's third law, the force applied to each coin is the same for the same amount of time interval, so the impulse must be the same. So which coin experienced a larger change in momentum? They both experience the same change in momentum because they both experience the same impulse. Impulse is change of momentum. Momentum is change. Momentum is, or change of momentum is impulse. Now, why is the effect of the same impulse different on the objects? Now, I give you a hint here. Impulse is change of momentum. So let's take a look at that. We know the force and the time interval that that force is applied is going to be the same. Now, so that means the impulse is the same, which also means the change in momentum is the same. But change in momentum is 2 different variables. I've got my mass and change in velocity. So that larger coin has a much larger mass, so it must have a smaller change in velocity. Now that penny or that smaller coin has a much smaller mass, so that's why the effect seems a lot different. Hey, it's the same force, same time interval, same impulse, same change in momentum, but because that smaller coin has much lower mass, it's going to have a larger effect. The change in velocity is going to be larger. So these are those questions, right? Which coin experienced a larger change of velocity and why? It's going to be the penny because the penny has a much smaller mass, or the smaller coin, which has more momentum. The small coin at rest on the table or the large coin at rest on the table, they have the same momentum. And the reason why is because momentum is dependent on mass and velocity, how fast they're traveling. This is kind of tricky. Which has more momentum? The small coin sliding on the table or the large coin sliding on the table? Explain your answer. Assume both coins have the same velocity. So now they have the same velocity, but that larger coin is going to have more momentum because momentum is mass times velocity. Explain what happens to the momentum of the coins during the collision. What you should get out of this is like sort of similar to air hockey table or like pool. That momentum is transferred. You slide a coin into another coin, you can see that momentum being transferred to the other coin. So now we know what momentum can do. Let's talk about what momentum cannot do. So in order to do this, we did collision cards. This was a simulation. So you can see here, have the answers over here. This is, we set up the different ones. Now, these were both explosion simulations, right? Where 2 cards were together, they exploded. And these 2 simulations, one was an elastic collision and the other was an inelastic collision. So what you should get out of this is the total combined momentum both before and after the collision were the same, right? So if you look back at these, notice, well, 10, 10 there, 10, 10 there. Okay, well, we've got 0, 0, and then 3, 3. The total momentum does not change between those carts. Now, the next one says, well, look at the simulations for elastic collisions and inelastic collisions. Well, how are they similar? How are they different? In both of them, the momentum before and after is the same, right? That's the total momentum before and after is the same for both elastic and inelastic collisions. Elastic collisions bounce. Inelastic collisions, those stick together. Now, the first simulation, how is it possible for the total combined momentum of the carts to be 0 kilograms before and after the explosion if the carts are moving after the explosion? So let's take a look at that one, right? So that's that first simulation. You'll notice, well, they're not moving before, well, the momentum 0, but they are moving after, well, 0. Well, it's because momentum is a vector quantity. So if they start with 0, you have to end with 0. If one's moving one direction, the other has to have the momentum in the other direction, and they balance out. So total, you're still going to have 0 momentum. Now, there are two things that cannot be done with momentum. Look at the simulations. What are they? You cannot create or destroy momentum. Those are the two things that cannot be done with momentum. You cannot create or destroy momentum. Explain what happens to the momentum of the carts during the collision. All that happened was the momentum transferred from one cart to the other, right? You cannot create or destroy momentum. You can just transfer it. So that brings us to that law of conservation of momentum. So in physics, the law of conservation of momentum states that when you have an isolated system with no external forces, the initial momentum of objects before and after a collision equals the final total momentum of the objects after the collision. In other words, momentum cannot be created or destroyed. It can only be transferred from one place to another. So I like to think of it as momentum is like cash in a room, right? It can change hands, but the total amount will remain the same, right? So if somebody gives, $20 to one person, that person gives $10 to another person, that person gives $5 to another person, that person gives $3 to another person, somebody spills a bunch of change all over the place, everyone goes and grabs it. Well, all that did not change the total amount of money in the room. All it did was it changed where that money is. That's similar to momentum. So let's take a look at some billiard balls, right? Does a cue ball have momentum as it's moving toward the remaining billiard balls? I mean, yes, it's moving, right? Do the unbroken billiard balls have momentum? Why or not? Well, no, they are not moving, so they do not have momentum. So what could you say about the total momentum of all the billiard balls on the table when you're comparing before and after the break, right? There's going to be the same momentum before and after the collision. So what happens to the momentum when the cue ball hits the unbroken billiards? Where is that momentum? It's in the other billiard balls. It just got transferred, right? That's it, right? The cue ball initially has all that momentum. Once it hits all those other pool balls, that momentum is in those pool balls. So we talked a little bit about this in that simulation. What is the difference between elastic and inelastic collisions? So a collision is any interaction that produces a change in momentum of an object. So there are two basic types of collision, right? We have elastic and inelastic. Elastic is bouncy, inelastic is sticky, right? I like to think of it as elastic, plastic, bouncy. So elastic collision, right? Here are some traits. There's no lasting deformation. So the objects don't permanently change their shapes. There's no heat generated during the collision, no sound generated during the collision. Objects tend to bounce off each other. Now, there's no such thing as a perfectly elastic collision, right? There are things that approximate an elastic collision. So here are some examples, right? Billiard balls striking each other, right? Tennis balls striking a tennis racket, a bouncy ball hitting the ground or the wall, bumper carts at the amusement park. These all are close to an elastic collision. But like I said, no such thing as a perfectly elastic collision. Now, inelastic collision are marked by these traits: permanent deformation, generation of heat, generation of sound. Objects tend to stick together. Now, you'll learn later that almost all collisions that are at least partially inelastic because of a concept we haven't learned yet, which is energy. So here are some examples, right? Piece of spaghetti thrown at a wall, right? Glass dropped on the hard floor, right? It breaks. Two football players tackling each other, right? So hopefully there's no permanent deformation, but they do kind of stick together because they like grab each other. Two cars colliding, right? Permanent deformation. So it should be understood that, like I said, there's no such thing as perfectly elastic nor perfectly inelastic. They lie somewhere in between. So I did have, now in this class, we're just going to assume that perfect collisions do occur. It's not like a 0 to 10 like I put down here, but I want you to see, like, if it's a scale between 0 to 10, most collisions fall somewhere in between, or some closer to one end or the other, right? So you can sort of say, okay, that's close to an inelastic, close to elastic in all of these. So let's go over some examples. Water balloon hitting a face. All right, so let's shrink this down here so you can see the scale. So let's take a look, right? Would this collision be considered elastic or inelastic? What can you say about the combined total momentum of all the objects when compared before and after the collision? There's going to be the same amount, right? So what happens here, this is going to be an inelastic collision because there's permanent deformation. That balloon pops. Now, it's the same total momentum, right? It just transfers from one object to another, right? Or it just gets spread out in all that water. But same momentum. It's just transferred, and you can see that it is going to be an inelastic because there is permanent deformation. So let's take a look at billiard balls. Like we already sort of went over this, right? So there's going to be I would consider this an elastic collision. There's really no permanent deformation. They sort of bounce off each other. Yeah, there is sound, but it is closer on that scale to a perfectly elastic collision. And that momentum just gets transferred from the billiard balls to each other. Let's do another one with tennis balls, right? So I would consider this one an elastic collision. Yeah, it does look like it gets deformed, but there's no permanent deformation, right? I would consider this more close to perfectly elastic. Now, like a bus hitting a wall or a car crash, well, I would consider this one inelastic. There's permanent deformation. It does make a lot of sound, does make a lot of like permanent deformation, a lot of sound, a lot of heat. And so this would be closer to the inelastic like scale. So those are just some examples of those types of collisions. Remember, there's too much unknown in the universe to take a break from learning. Get out there and question everything.